All too easy to tip over. Good luck. I'm talking with you at 2 o'clock, by the way.
Very good. I'm looking forward to it.
Thanks, Anthony. All right, I think we can go ahead and get started while people continue to trickle in. So today's colloquium speaker is Earl Bellinger. Works a lot on astroseismology and dabbles a little bit in primordial black holes these days as well, as you'll hear if you come to ITC lunch. Earl did his PhD, I believe, at the Max Planck Institute for Solar System Research, technically in computer science, although I think it was pretty astrophysics-y. Since then has been a postdoc in Aarhus at the Stellar Astrophysics Center, and most recently at MPA in Garching, and has just started as faculty at Yale, I think just about a month ago, right, in January. So he's just down the road now, and will be telling us some about astroseismology this morning. So take it away, Earl.
Thank you very much, Evan. That's very nice. So I'm extremely honored to be here. Thank you very much for inviting me. As Evan mentioned, I am just down the road now. So part of this talk is trying to maybe inspire you why you might want to use astroseismology in your research, and maybe we can start collaborating on some topics in the intersection of astroseismology and whatever it is that you work on. Because I'd like to make the pitch here today that astroseismology is extremely valuable for astrophysics, that the ultra-precise measurements that we've been getting over the past decade and will be continuing to get into the future, these ultra-precise constraints, we can then lend them to other fields of research and provide constraints there as well. And in particular, today I'm going to be taking you through quite a number of different topics that I think astroseismology is useful for. But before we jump in, let's talk some history. So in the 1960s, some researchers at Caltech pointed a spectrograph at the sun and discovered that the sun is a variable star. This came after about 400 years of variable star research. And it wasn't really known at this time what they were looking at, although they did speculate already in 1962 that these were global oscillation modes. And indeed, it took a couple decades to work out the theory, but in fact, we now recognize these as global oscillations. Modes of high spherical degree are confined to the outer layers of the sun, whereas modes of low spherical degree probe the near core regions. And so observations of these different modes grants us insight into the internal structure of the sun and can be used to not only measure its structure, but also compare it with theoretical models. So these measurements have revealed the solar structure and told us that our theory of stellar evolution is approximately correct in predicting the stellar structure. So the sun, of course, has a core that has been converting hydrogen into helium over the past 4.5 billion years. In the inner regions, energy is transported by radiation, and in the outer regions, energy is transported turbulently by turbulent convection. And this turbulent convection is responsible for exciting the oscillation modes in the first place. They dump energy into the normal oscillation modes of the star and cause it to oscillate with a characteristic period of 5 minutes. So very, very short time span. And so therefore, in order to resolve these oscillations, you have to observe the sun more frequently than those 5 minutes. And then you can do a Fourier analysis and these oscillation modes appear. And so this allows us to test solar evolution theory. You can make standard solar models, one solar mass, with the luminosity of the sun, radius of the sun, age of the sun, and calibrate the protosolar conditions, so like the protosolar chemical abundances, and the theoretical parameter, like the mixing length parameter, that determines the efficiency of convection. And you can make models of the sun and then contrast those models with the structure of the actual sun. And most of the rest of the talk will be saying, okay, how do we go beyond the sun and do this for other stars? But it's worth taking a look at what's been done for the sun. So this was a really great paper from Jørgen Christensen Dausgaard in 1993. I did my first postdoc with him, expanding this kind of research to other stars. And what JCD did was he constructed several different solar models, age of the sun, mass of the sun, et cetera, but with different ingredients in the input physics. In particular, he tested out models that have diffusion, which is the settling of heavy elements into the interior of the sun, and models that don't, with some different prescriptions. And here on the y-axis, you can see a comparison. These are the differences in the internal structure of the sun as compared to the structure of these solar evolution models. And what you can see straight away, the scale is 1%, right? So this tells us that our solar evolution models are in absolutely phenomenal agreement with the data, better than 1% accuracy at resolving the solar structure, which is basically a miracle by astrophysical standards. This is just an astonishing confirmation that nuclear fusion is driving the evolution of the inside of the sun, and that the sun has this outer convection zone that's transporting the energy in the outermost 30% or so by radius. And so the other thing you see from this diagram is that the models with no diffusion are in much more tension with the observations than the models that include diffusion. And so, yeah, these are the set of models that include diffusion, and this one doesn't. And so, I mean, all the models are pretty good, but these ones that include diffusion are definitely better.
How big are the error bars on the measurements?
They're so small that you can't really see them. Actually, that leads to the next very interesting point here, which is that all of these models and solar evolution models today are in extremely significant tension with the observations. It's just at an extremely tiny level, right? So qualitatively, the model is absolutely right. It's a great model. But quantitatively, statistically, it's something like 60 sigma away. And we basically know where these problems are located. This is the base of the solar convection zone at about 0.7 or so solar radii. And yeah, convection's hard. Determining the base of the convection zone is hard. The shear layer below the convection zone is difficult to model. We also have problems with the near surface regions. We have problems with potentially the opacities, determining the base of the convection zone. And several other uncertainties, for example, in microphysics might pile up. And then you might also get effects that come from the fact that we're modeling this as a perfect non-rotating sphere, without any magnetic fields and so on.
Yeah, I'm kind of amazed you can do that well when it's not rotating.
Yeah, exactly. It's astonishing. The rotating models don't actually improve things so much because the sun's a very slow rotator. There's been a lot of hints at what could possibly improve the solar model. That's not really the topic of today, but it's a very interesting topic. One potential improvement could come from more accurate modeling of the star and planet formation processes, because here you assume that the star had its total mass at birth and just kind of collapsed to become a ZAM star, but that's not really realistic. Instead, it actually accretes up to its current mass over time. And also, during planet formation, it might also ingest metal pore gas, which means that the metallicity of the core might be different than the metallicity at the surface upon its birth. So those kinds of details could improve the model. That's all to say that we have an astonishingly accurate model, and certainly from the point of view of other stars, this is just fantastic. So for a long time, the sun was the only known solar-like oscillator, and that should be intuitive because it took us till the 60s to determine that the sun is an oscillator. And that's because the solar surface is moving by something like a meter per second. I mean, it's just a really tiny variation. These amplitudes are extremely small. But thanks to space missions like Corot and especially Kepler, we've started to detect these kinds of oscillations in other sun-like stars. So today, we presently have something like 100 really good solar-like oscillators from the Kepler mission. But in the future, this number should rise. Yeah, this indicates the rise from TESS. Actually, this is slightly misleading. We've detected solar-like oscillators with TESS, but resolving the individual oscillation modes is really difficult, and TESS isn't able to do that for sun-like stars. But soon we will have, wrong direction. Soon we will have the Plato mission set to launch in a couple years. So I'm one of the people working on Plato, and we're going to dramatically increase our sample of solar-like oscillators. Asteroseismology is moving into the big data era. And the best yield will be for red giant stars. The luminosities of, the amplitudes of solar oscillations scale with the luminosity over the mass. And so going to the red giant branch, not only are the stars themselves much more visible, you can see them at much greater distances, but also the amplitudes of the oscillations are much higher.
Frequencies for giants?
They're about, the periods are like hours. The frequencies are like 200 microhertz.
Okay. Oh, I would have thought this guy being so big, its frequencies would be awfully low.
Yeah, I mean,
Is it because the spherical order is?
it just comes from the mean density of the star. Periods scale with root mean density. Yeah. So, and we're set to expand the number of sun-like stars that have resolvable individual modes up into the, let's say, 10,000s with Plato. And then for red giants, it'll be something like 10 million stars with individually resolvable oscillation modes. So the future is very bright for astroseismology. So that gets me to the next point of what can we do with this data? So I'd like to show you an example of Kepler time series. So this is just 1 week of photometry from Kepler. And you can see that the variation is really small. Like these points don't have uncertainties on them, but this is actually all pure signal. This is not random noise. And so when you look at it in this view, you can't really see anything. But if you take a Fourier transform, then clear astroseismic signal emerges. So each of these peaks here is a unique low degree mode of oscillation. I've indicated which ones we can identify as being oscillation modes. So this particular star is observed to oscillate in about 50 different unique low degree modes of oscillation simultaneously. And if you remember, the low degree modes are the ones that probe the core of the star. So nature has been kind to us. Instead of just giving us, the skin condition of the star, we can actually look into the cores of these stars with astroseismic measurements. So you can see that there's a clear pattern here. Modes are roughly separated by a characteristic separation that we call the large frequency separation. I think I have, okay, this is showing you what such an exaggerated view of what such an oscillation might look like. So these are quadrupolar oscillations shown in blue. And then if we zoom in on the spacing, so the modes are roughly spaced by this thing called the large frequency separation, which tells us the mean density of the star. And then there's also this spacing between the 0 and 2 modes that's called the small frequency separation. The very interesting thing about the small frequency separation is that this turns out to probe, and you can show this. This turns out to probe the mean molecular weight gradient in the core of the star. And that's very interesting because obviously sun-like stars are converting hydrogen into helium, and so that gradient is changing as the star evolves. And so this thing gives us a direct probe on the helium abundance of the core and therefore the age of the star. And that's why astroseismology is enabling precise characterizations of stellar ages. The next step is to connect these observations of solar-like oscillations to theoretical stellar models. So here's some evolution. Oh, I pressed the wrong button. Here's some evolutionary tracks of sun-like stars and observations from the Kepler mission of where they fall on the HR diagram. And then over here is what we can do with the astroseismic data of these objects. So this is a so-called Christensen-Dowsko diagram after the guy who came up with the idea back in the 80s. The point is that you plot these two quantities that I just told you about, the large and small frequency separation. And that gives you basically like a lookup chart of the properties of the star. So here's theoretical evolutionary models starting at 0-age main sequence and evolving until core hydrogen exhaustion. And these are tracks of different masses. So here's the sun at its birth, and it evolves and it gets its present value here, and then it goes until the end of the main sequence. And you can see that you can just basically look up the values of the large and small frequency separation, and that uniquely tells you the mass and chemical composition. And down here in the corner, I've indicated the typical level of uncertainty on these measurements of the large and small frequency separation, and you can see that they're absolutely tiny, like smaller than the size of this symbol. So it gives you a really great view on the internal structure of these stars. Now, of course, in this view, this is only a two-dimensional view. The only things I'm varying here are the mass and the age of the star. There's a lot of other theoretical ingredients you can put into a stellar model, like the metallicity, initial helium fraction, efficiency of diffusion, efficiency of convection, and so on. And so for that, we want to model things in a much more sophisticated way. And so for that, we use the MESA Stellar Evolution Code, of which I'm one of the more junior developers. I joined the team a few years ago. As you all know, Evan is one of the more senior developers. I don't know how long have you been with MESA?
Oh, I guess 10 years.
Yeah, so.
Early in my PhD.
Yeah, so we just had our most recent instrument paper released. We're going to release a new version of MESA tomorrow. I'm actually the release manager for that one, so that's kind of exciting. I guess you all know MESA very well, but it's worth pointing out that this is one of the most visible projects in astrophysics. Been cited many thousands of times, and the papers that cite MESA have been cited many, many, many more thousands of times. And we do a lot of activities like putting on summer schools and supporting our users with our mailing list, and maintaining the code, fixing bugs, and implementing new physics into the models, and providing infrastructure for continuous integration testing of all the new capabilities. We're an open source code and try to be a good example of one, so we welcome your contributions and your involvement. Okay, so what I did was I constructed an extremely large grid of theoretical stellar models that span all of these dimensions simultaneously. I mentioned mass, age, but also things like different chemical compositions and efficiencies of mixing, different prescriptions for overshooting and extents for overshooting of convective boundaries, and so on. I think I made the most high-dimensional and largest grid of stellar theoretical stellar oscillators ever made. And then put this into machine learning machinery in order to infer the properties of stars while propagating through the uncertainties of these theoretical model parameters. So this is just a schematic view of one way of possibly doing this. On the left, you put in your data for your star, like your spectroscopic data, your astroseismic data, and optional other data that you might have. Maybe you have, maybe you have like interferometry of the star, or you have some Gaia measurements or something. You pass it through a machine learning algorithm, and out comes posterior distributions on age of your star, mass, composition, and whatever else you want to learn about the star. So that's kind of a schematic. Here's one example of how we did this for subgiant stars. So I worked with Mark Hahn, who he was a Hubble fellow. So I worked with him during his, he was a PhD when he worked with me, PhD student when he worked with me on this. And then he was a Hubble fellow, and now I think he's next door at MIT. I'm pretty sure. Maybe. And then as the output layers, we have a mixture density neural network, and so you get distributions of the outputs. So you don't just get like a value for an age and maybe a standard deviation, but you can actually get a full distribution on the output. There's a lot of different takes you can do on this problem. You can also train, for example, a neural network to be an emulator for stellar evolution calculations, and then sample that emulator using MCMC. It's another possible way to tackle this. So what do we get from asteroseismology? Well, we've applied this to the 100 best stars from the Kepler mission, and these are the kinds of uncertainties that you get out when propagating through all of the theoretical uncertainties that we know how to propagate through. As well as the random error from the observations. And what you see is that we constrain surface gravities extremely well to like 0.1%. Radii of stars we get to about 1%, masses of stars we get to about 4%, and ages of stars we get to about 10%. And my claim is that these measurements are extremely useful for astrophysics and are helping to drive a revolution throughout many different fields by lending these ultra-precise radii, masses, and ages. So, what can yeah, please.
On the last side,
Yeah.
how does that depend on the number of modes that you can observe?
Yeah, that's a very good question. I have a slide later about the development of techniques that work on very low signal-to-noise data. So I'll show you that when that comes. But these are all 4 stars where we can resolve at least, let's say, a dozen individual oscillation modes. Nice hoodie, by the way. Okay, so now this next part, let's see, I'm about 20 minutes in. I'm going to pretty briefly go through most of these because in the interest of time, but of course we can talk more about any individual topic if you like. So exoplanets is a clear application, and the reason is simply because if you measure an exoplanet using the transit method, then you need the depth of the transit, but you also need the radius of the host star in order to constrain the radius of the exoplanet. And so to leading order, the number one thing that the exoplanet radius uncertainty depends on is just the stellar radius uncertainty, right? And here's the region of radii uncertainties that we can get with asteroseismology. And so the very best constrained exoplanets are the ones for which their host stars has been characterized using asteroseismology. And then you can do things like take those measurements that you get, and you can also throw that into a neural network that's been trained on planet evolution models, and you can then put some constraints on what the internal structure of those planets might look like. And this is work that I've carried out with Simon Albrecht and an undergraduate student in Denmark, Silke Denies. That's all I want to say about exoplanets. So I'll just move right on unless someone has something else. So the next topic I'd like to talk about is galactic archaeology. So galactic archaeology is the study of trying to understand how our own galaxy formed and evolved over time. And in order to carry this out, we need a few different ingredients. We need the positions of stars, we need how they're moving through the galaxy, we need their chemistry, and we need their ages. If you take those ingredients together, then you start to get a map of how the Milky Way developed over time. Now, these things are now being provided in bulk. So we got astrometry from Gaia, we have spectroscopy from large-scale surveys like Apogee, and we're getting ages from Kepler and then soon TESS. Now, the point here is that our best astroseismic data comes from Kepler, and Kepler looked at one fixed field of view of the sky for 4 years. It's like this tiny little postage stamp. So basically everything we know about solar-like oscillators comes from like 100 stars in Cygnus. That's it. That's the whole sample. And then you know, maybe tens of thousands of red giants as well. Kepler then started to wander the galaxy, so that's the K2 mission. But the data quality, it was good, but it's nowhere near as good as the nominal 4-year mission of Kepler. But in a couple years, we're going to have the Plato mission, which is going to give us 200 gigabytes of data a day looking at most of the sky. And so this is going to be an absolutely fantastic mission for galactic archaeology, allowing us to determine the ages of 10 million stars throughout the galaxy. And you know, maybe we take it for granted now, but it was only about 5 years ago when we discovered that the Milky Way was formed out of a major merger with the Gaia Enceladus sausage, very unfortunately named. But I mean, this is just a field that's exploding with discovery. And also, it was recently discovered that most of the halo population was accreted ex situ. So it's just an incredibly amazing field for discovery. So this now gets to your question on extending the reach of astroseismology. So we're going to get this amazing yield from the Plato mission, but most of those stars we won't be able to resolve the individual oscillation modes for. So the question is, what can you do for this vast majority of stars for which you only see the characteristic frequency at which the oscillations are excited, but no more details than that? So that's this quantity called Numax. And here, just one example of how we can extend the reach. It turns out that Numax scales, the radius scales with 1 over the root of Numax, and you can get uncertainties of red giants to 6% just by measuring that one quantity, which we should be able to do for at least these 10 million red giant stars. You can also get ages of of these red giants to about 10%, but you also need to measure the characteristic spacing between frequencies, for which you actually don't need to resolve individual oscillation modes. You can just take, if you have your power spectrum of your oscillation modes, you can just take a power spectrum of that, and that characteristic spacing will be a peak in that periodogram of the periodogram. So even with very low signal-to-noise data, we can get ages to 10%. Pretty astonishing. And then this ultimately will allow us to test cosmological zoom-in simulations that are predicting the formation of Milky Way-like galaxies. We're going to be able to compare our observations of the Milky Way with mock observations of these galaxy formation simulations. We'll be able to put in different physics into the galaxy simulations and see what effect that has on creating the Milky Way. But it goes even further. So I mentioned that these solar-like oscillators have very low amplitudes, so you can only really see them in the galaxy. If you wanted to see something like the sun in the Milky Way pulsating, you need something like a 100-meter telescope on the moon, which I suggest we do, but I don't think we get the funding right now. One question is, what about the classical pulsators? Well, most people, many people have been working on, I mean, this is one of the oldest fields of astronomy. But the problem with the classical pulsators is you only get one period of pulsation. What can you do with just one period? Well, it turns out that not only do you get this one period, but the light curve of the star has this characteristic shape. It doesn't look exactly like a sine wave, but it's slightly deformed. And the deformation from a sine wave is actually telling you something important about the internal physics. And so normally in astroseismology, we only look at the frequencies of oscillation, but here I'm looking at the shape of the light curve itself. And it turns out that when you train these machine learning models on the shape of the light curve, that you can actually estimate the masses of Cepheids, which is not normally very well possible unless they're in a binary or something like that. You can also do this for R. Lyrae stars. And so with the forthcoming LSST mission, we're going to be getting R. Lyrae stars out to half a megaparsec. And that will allow us to characterize basically the complete dwarf satellite population around the Milky Way. So we're going to be able to do extragalactic archaeology with classical pulsators. That's why I named this paper When a Period is Not a Full Stop, which is a joke that nobody got. One interesting side consequence of this is that of using these machine learning models is that you can actually start to get some insights about stellar physics by trying to inspect what the machine has learned about your problem. So in this particular example, we noticed that when we wanted to estimate the temperature of a star based off of the shape of its light curve, it turned out that the most important thing in determining the temperature of the star is not the period of pulsation, right? It's actually the second amplitude component in your Fourier decomposition. So I said it looks like a sine wave, so the main component is the amplitude of the main sine wave, but then you have additional components at double, triple, and so on. The frequency explaining the derivations from a pure sine wave. And it turns out that the amplitude of this second component is a sensitive probe of the temperature. And so we saw that and we looked at the data, and indeed you can see that as a star passes through the instability strip and changing its temperature through the while, the amplitude of this second harmonic component is changing more or less monotonically with that. So that starts to give us some hints at what's going on and why we get these nice constraints. Which leads me nicely into the next topic of stellar physics, which is, of course, the main yield from asteroseismology. If we have any questions on that, okay, then I'll just go on. Okay, so as I mentioned, asteroseismology allows us to look inside of the star. So most of what I told you before was talking about how we can get things like the mass, the radius, and the age of the star based on the seismic data. But in fact, for the best observed stars, we can look inside the star and get seismic measurements of the interior. And so what can we do with that? Well, One thing is that we can measure the size of the convective core. So stars like the sun have no convective core on the main sequence, but just as soon as you start to pump up the mass a little bit, you get a smaller and then a bigger and bigger core. And so a lot of people think that stellar evolution is a solved problem, but one of the main uncertainties is the size of these convection regions. Typically, this is just parameterized in an ad hoc way by adding some overshoot beyond the convective boundary, because we know that the boundary given by mixing length theory is not really a physical one. And so with astroseismology, you can start going in and measuring the sizes of these convection zones, which then provides valuable inputs on what stellar evolution theory should predict. And so here we've measured how the convective core should grow as a function of mass using seismic data. Another thing you can start to do is look at the rates of nuclear reactions, because this, of course, has an effect on your inner structure. So here with Jørn Christensen Dausko, we made the simple point that the seismic data of the sun is actually better at constraining uncertain nuclear physics than the nuclear physicists have given us. And that's because the internal density profile of the sun is so precisely constrained. You remember I told you that it's basically known to better than 1%. Well, if you change the initial reaction in the pp chain by more than 1 sigma, then you change the internal structure of the sun by several percent. And so in principle, we can use the sun as a, it is a nuclear reactor, right? So we can use that to study nuclear fusion. And one thing that I'm excited about going forward is coupling these kinds of measurements with measurements of other stars, basically using an ensemble of stars to say, hey, nuclear physics doesn't change from one star to the next, so let's fit all of these stars simultaneously and see if we can get an even stronger constraint on the nuclear reaction rates. But here, it's looking like we might be able to get a 7 times improvement on the slowest rate in the pp chain from helioseismic data. Okay, I mentioned earlier that we can look at the structure of the sun using seismology. What about the structure of other stars in detail? Well, we only get the global modes. We don't get the modes that are confined to the outer regions of the star, and so we won't be able to resolve anything about the outer regions. But for the near core region, we can make measurements of the inner structure of the star. So just like we did with the sun, here's the difference in the internal structure between the star and a best fitting stellar evolution model as a function of the fractional radius. So here's the center of the star, and here's like halfway through the star. And we can measure the difference in the sound speed with about, around 5% uncertainty between the star and the stellar evolution model. So the uncertainties are much greater than in the case of the sun. So uncertainties in the sun were much less than 1%, and this is quite a bit more than 1%. And what we basically see is that the structure of this star is in very good agreement with best fitting stellar evolution model. Yeah.
Is the fact that it's 5% because you don't have enough modes, or because we haven't observed the star long enough to split the modes?
Right, no, actually, this is the best observed star that we have. There's about 60 oscillation modes in this star. But it is, in fact, the number of modes that's hurting us and not having these high degree modes. So observing this star for longer won't actually help anything. You would need something like a space interferometer to resolve the disk of the star. And that's because these higher degree modes get geometrically canceled out in integrated starlight. So for now, this is basically what we can do. And this won't improve with Plato either. We need better technology. So for this star, which is a very sun-like star, it has actually, as far as we can tell, the mass of the sun plus or minus like about 1%. So it's extremely sun-like, and it's just like a couple billion years older. So an extremely sun-like star. Let me just check my time. Okay. So for this star, we find very good agreement. Now, my first PhD student has just published their first paper in which they've analyzed the rest of the sun-like stars in the Kepler data and found a few stars for which our models are in highly significant tension between theory and observation. And so these might be some indications that we have some ingredients that aren't quite right in stellar evolution theory. And if you look in this paper, we point to some CNO reaction rates that if you change them, it can make a dramatic improvement to the differences in internal structure between the seismic measurements of these stars and the models of these stars. We looked at some more massive stars with like a small convective core, not very massive, it's like 1.2 solar masses. And again, we see some tension, but we weren't able to actually identify the source of this tension as coming from the convective core. So we played around with overshoot and with diffusion and other such ingredients we could put in, but we couldn't make the structure of the star match, the structure of the model match the structure of the star. We started looking at subgiant stars, which are extremely interesting because they have mixed oscillation modes. So the sun only has P mode oscillations. It probably also has G modes, but they've never been discovered despite many claims to the contrary. But when a star evolves into a subgiant, then the G modes they're trapped in the core of the star begin to couple with the P modes that are in the outer layers, and you form a mixed mode oscillator that grants you really interesting insights into the deep central regions of the star. In our own sun, we can only resolve down to about 2% away from the center point, right? So the innermost regions of the core, we can't measure even in the sun. But in subgiant stars, we can actually make measurements in the deep, deep interior. You see this is much less than 1% inside the star. The other somewhat shocking thing about this is that the discrepancy here is so great. This has an internal sound speed profile that the seismic measurements are telling us the sound speed is much lower than in the model. And because the sound speed monotonically increases along the subgiant branch and the envelope is in pretty good agreement, this appears to be a young star encased in an old envelope. And who can't relate to that? Okay, the other amazing yield from the Kepler mission is measurements of rotation rates from Asteroseismology. And they've revealed that our models of angular momentum transport in stellar interiors is extremely deficient. We can't predict how stars will rotate over time, and so it's an area where we need a much better theory. But also we need better measurements. So what Felix Albon showed in this paper, so Felix worked with me since he was a bachelor student, now he's a postdoc. Felix showed that the method that people have been using to infer the surface rotation rate in red giant stars is actually plagued by systematic errors. So this old method, when you try to estimate the surface rotation rate of the star, you're getting the core rotation rate contaminating it. So the cores of red giants are spinning extremely fast because the envelope puffs up and the core contracts, so you spin it up. And that fast spinning core made us think that the surfaces were a different velocity than they really were. So we developed a new method that eliminates that cumulative sensitivity, and now we can provide reliable measurements of surface rotation rates in red giant stars from Asteroseismology. Okay, I see that it's 11:40, so I think I'm going to mostly skip the next topic. I don't know exactly when I should end, but maybe like 11:45 or so? 11:45. Okay. Okay, I'll say one quick thing about binary stars. So we just submitted this paper, which I think is pretty interesting. So mostly I've been telling you about low mass stars, but actually you can do astroseismology with higher mass stars too, not just Cepheids, but also main sequence stars. So these are B-type stars, so like 10 to 20 solar masses, as you can see in this HR diagram. And these are theoretical stellar evolution tracks, and they're colored by how long they live in the HR diagram. So this is the main sequence, and then you cross the Hertzsprung gap in a really short phased live of stellar evolution, and then you become a longer lived red giant star. And so according to this picture, you should see a ton of stars here, and no stars here, and then a ton of stars here again, right? The difference in the occupation of stars here versus here should be like a factor of, I don't know, 1,000 or 10,000 or something like that. But actually you see very similar numbers of stars here as here. And so this is a famous problem in stellar astrophysics known as the blue supergiant problem. Why do we have all these blue supergiants that are just hanging out here in the Hertzsprung gap? It doesn't seem to make any sense. Well, one attractive solution to this problem is that these stars might be long-lived binary merger products. Now, at first glance, that might seem like a preposterous hypothesis. That's what I thought at first, at least. But in fact, most massive stars are born in binaries. The binary fraction is something like 100%. Single stars at this mass are the exception, not the norm. And something like 1/3 of those stars will merge over their lifetime. So what we did in this paper is we constructed theoretical stellar evolution models of merger products. And we did a very flexible and general parameterization that we thought spans probably a very wide range of possible merger outcomes. And here we're showing one slice of parameter space of the kinds of mergers that you would get. So the star merges at this point, and then it does this little loop, and then comes here and becomes a core helium-burning star and lives for example, maybe a megayear in this position. And this color scheme is the same as this color scheme, and so you get some long-lived stars right here as blue supergiants. And so, well, we haven't solved the problem yet. In fact, all we've said in this paper is a route towards potentially solving the blue supergiant problem. With the point being that in this paper we show that these stars, because they have a dense helium core, would have very different properties than these Hertzsprung gap crossers that classical stellar evolution theory predicts. And so if we're able to do seismology of these stars, and we've been working with some observers, but it's hard. We've been trying to measure the seismic signals in blue supergiants in order to see if we can extract the measurements. But if we can, then that would allow us to distinguish these cases. There's actually a couple other cases. You could extend the main sequence lifetime with dramatic amounts of overshooting. And also, you could have a blue loop during the red giant phase that would also give you core helium-burning stars in this region of the diagram. And so our point in this paper is that if the observers are able to deliver us some astroseismic measurements of these blue supergiants, then those seismic measurements will be sufficient to distinguish these cases.
So in this story, there is no red giant branch at all?
Oh, sorry, this would continue on. I've just clucked it, yeah. Yeah, actually, these are cool because these, they do become red giants, but they also, some of these models are like good progenitors for supernova 87A. So this is like a likely scenario. According to the supernova folks, they think it's a blue supergiant progenitor, probably from a binary merger. So, but that's not my field. Okay, that's basically what I want to say about that. I'll skip through all this stuff. Okay, I just want to say one fun thing before I end. So this is maybe a more exotic application. So, according to Einstein's theory of relativity, the gravitational constant is indeed a constant across all space and all time. But theories of modified gravity, like string theory, promote the gravitational constant to a dynamical quantity that varies over time and space. And you can even look at some papers on individual string theories, and they will predict a rate of change for the gravitational constant over cosmic time. Well, from my point of view, this is an empirical question that we should be able to test. And what is a good test of that? Well, there's actually a few really good tests. One is the lunar ranging experiment. The Apollo mission, they set up these mirrors on the moon. You can send lasers there. And from solar system dynamics, you can track the secular evolution of the gravitational constant over the past few decades. And that constrains it extremely tightly, more tightly than we can do. You can also do it based off of binary stars, especially binary neutron stars. Pierre Demarque at Yale in 1994 suggested the sun as a laboratory for testing this hypothesis, with the idea being that you could model the evolution of the gravitational time over the lifetime of the universe as some kind of power law, where the G evolves over time to get its present value at today. And then the game is trying to measure this evolution parameter beta, which tells you how it evolves. So here's an HR diagram telling you what the evolution would be like for different values of this parameter beta. And there's some intuition that is helpful here, which is that the luminosity of a star scales with g to the power 7. And so stars that live some of their life in, with a stronger or weaker gravitational constant, they would have been supplying much more or much less luminosity, which has an effect on the resulting stellar structure. And so the present day population of stellar structures that we observe, in principle, puts limits on the range over which the gravitational constant could have varied over cosmic time. So we took one of the oldest stars in the galaxy. It's about 11 billion years old, so more than twice the age of the sun. And we did a similar game as before. We constructed a huge grid of theoretical stellar models spanning all the uncertainties that we can think of, including the uncertainties in nuclear reaction rates, because, of course, this would be degenerate with changing rates of nuclear reactions, which controls the age of the star. We did a big MCMC simulation across that parameter space, and we were able to constrain that the gravitational constant varies by no more than 5 parts in a trillion per year over the past 11 billion years. So far, no evidence from astroseismology for string theory. The last thing that I will be talking about today won't come right now, but it will come soon during lunchtime, in which I will be talking a little bit about how we can use astroseismology to constrain dark matter. So in summary, astroseismology is providing extremely precise constraints on mass, radius, and age, which is driving a revolution throughout many different fields of astrophysics. It allows us to precisely characterize exoplanets. It's allowing us to characterize not only our galaxy, but also the satellite galaxies around the Milky Way. It's allowing us to test the theory of stellar evolution in detail, such as the physics of stellar cores, how convection really works, rotation, and other things. We're going to be able to get some insights on binarity and the evolution of binary stars from astroseismology. And it even allows us to probe some revolutionary physics, such as the stability of the fundamental constants. So thank you very much for your attention, and I look forward to talking with all of you.
So we have about 10 minutes for questions, and I also, while I remember, I want to say Earl's here today and tomorrow. That's right. So I sent out a schedule, and there's still space if you want to sign up to talk to him this afternoon or tomorrow. So anyway, yeah, any questions?
Should I run the mic?
Yeah. Go ahead.
I think this is on.
Terrific talk.
Oh, it's not on. I don't know.
Okay. How about that?
It might just be off.
How about that?
Still not.
We don't need these.
Okay.
It's not a very complicated question.
Okay.
Cepheids, the fundamental mode pulsators are pretty well behaved, which we learn a lot of things from that. On the other hand, those that are pulsating in the first overtone have some examples of bad behavior. And I've always wondered whether the mode in overtone pulsating must be higher in the envelope, and maybe it's less well confined. So I just wonder if you had any comments about that.
Oh, that's a great question. Yeah, I've been working with a PhD student, Mami Deka, on making a comprehensive grid of time-dependent pulsation models for Cepheids, and we've been looking at the evolution of the first overtone mode and where in the instability strip this starts to get excited and what we can learn from studying those modes. But I don't actually have some insights that I can think of off the top of my head. But I'd be very happy to talk with you in more detail about this. It's a great question. Thank you.
I want to go back to what I asked earlier, because I was confused by your answer.
Okay.
So you said red giants will oscillate on hours time scale. To me, it seems like it should be months. That's the sound crossing time. So I'm kind of missing something here. The guy is big, right?
Yeah, sure.
But the F mode would be, the fundamental radial mode would be daily.
Oh, right. Okay, that's the point. These red giants aren't observed to pulsate in the fundamental like in Cepheids. They're observed to pulsate in, like, let's say the 10th overtone, and the spectrum around that 10th overtone. And so you have many multiples of the fundamental frequency. Yeah, so a typical frequency is around 200 microhertz for, let's say, a one solar mass red giant for which we can observe seismic frequencies. Yeah, thanks for that catch. Yeah.
I have a few questions, and I want to add a little bit about the Cepheids before I ask my question.
Sure.
Currently, I'm working with a group of ONI, and we're trying to find a rotation mechanism in one of the beta Cepheids. And we see that for the first overtone, there are actually cases of accidental degeneracies.
Say again?
Accidental degeneracies, meaning like if you let's say solve the eigenvalue problem, you end up with nodes which are very close, and you probably need to account for both of them together while doing inversions. So they can be completely different rotation profiles actually.
Yeah.
Anyway, for Plato, do we expect to get enough resolution so that you can look at the splittings of L equals 2 and you can start using the quadrupolar modes for inversions?
I have strong doubts. Plato is a fantastic successor to Kepler, but in many respects it won't exceed Kepler, and not even Kepler could measure the splittings of L equals 2 modes. Probably the most promising for that are the long time series ground-based networks of spectrographs, so that's the SONG network. That actually gives us the best seismic data available, especially because it can do such a long time series. You know, the best SONG target has something like 10 years of observation, so more than twice the length of Kepler. But even with that data, I don't know if we have any measurements of split L equals 2. Actually, there might be like a handful of measurements of split L equals 2 modes. I know papers by Sebastian de Heuvel's that at least does the theory of the nonlinear splitting of the L equals 2 modes. But the observations are quite rare. So I don't think we'll get a lot more with Plato. But it's a great question. I mean, that's something, so soon we're going to be getting the mock Plato data set, and then we can just simply look to see if it's of sufficient quality to see split L equals 2 modes.
Yeah. So the main reason why I ask it is because with L equals 1 splitting, you can probably, if you're trying to resolve internal structure, you can do pretty well for some sort of rotation profiles, but as soon as you go to like structure sort of magnetism, you need to start looking at L equals 2 splittings.
Yeah, certainly.
Another thing I wanted to ask was for one of the slides, I forgot which one, where you were working with one of your PhD students to constrain the internal structure. There is something special about approximately what you have there. Here on the next slide, there's something special with the structure of the star at around 0.2 stellar radius. You tell us what constrains the inversions that well over there?
You're saying right here?
Yeah, right.
Oh, you're noticing that the error bars are smallest here.
Yeah, and also in the previous figure. So just
Yeah, absolutely. Yeah, I mean, this is basically the region that's just probed best by the available seismic data. It just so happens that this is the sweet spot when you look at sun-like stars. Also, if you were to take the sun and remove all of the modes greater than L equals 3, you would see that, I mean, you can see this intuitively. If you, in addition to your eigenfrequency, you have your eigenfunction, which tells you how the star is being displaced from the oscillations. And in order to do this kind of inference, you take a linear combination of those, I'm hand waving a little bit. You take a linear combination of those displacement eigenfunctions, and because the modes have a similar geometry in the outer regions, you can cancel out their eigenfunctions. And in the inner regions, basically, it turns out that this is the region that is exactly probed best by low degree solar oscillation data.
These kernels have the most uniqueness
Yeah,
in that region.
that's right.
And the last thing I wanted to ask was for your student to improve the rotation measurements. Yeah. So how are you parameterizing the rotation? Normally, I know that it's a step function that you
Right.
have to choose, right?
Yeah.
So do you know where you want to break the
Yeah, that's a great question. So basically, all red giant asteroseismology, of internal rotation inferences, rests on some kind of assumption of an internal rotation profile. Another thing we show in this paper is that if the rotation profile is significantly different than what everyone else assumes it to be, this doesn't work at all. So here, we're using a step-like profile, and the step is at the core boundary. So the core is rotating fast, and then if I were to draw it, it's something like you have a fast rotating core here, and then it falls off like linearly, or it falls off with like a power law. We test out different models. But if you put the boundary somewhere else, like, yeah, so you can put the boundary, for example, like in the hydrogen burning shell, or at the base of the convection zone, or you can play around with that. So that's what we did. We played around and said, what are different possible rotation profiles? Your inference can fail catastrophically if you have like, if red giants are actually rotating with a very different profile than what we expect. Now that being said, that limitation's not there for the sun, so we can measure the internal solar rotation profile pretty reliably without making these kinds of assumptions. We know the solar convection zone is differentially rotating and that the radiative interior is rotating like a solid ball. So that's some indication that that kind of shape will evolve into the future, and that having this kind of two-zone profile is probably not the worst approximation ever. So there's probably some errors you introduced by having this assumption of what the internal rotation profile could be like, but at least my prior is that it wouldn't be so far off from this reality based on what we know about
I was just
this one.
gonna, like, my question probably, that was the answer, but I was asking if you did something like an MCMC where you actually allowed for the boundary to also be an
Right.
inversion parameter instead of like fixing it and then trying to infer the steps.
Right. So we've actually tried this kind of thing, and someone else even we didn't publish the MC analysis, but Thomas Bellinger did one where he did that kind of thing, if I'm remembering correctly. I think you actually get nothing out because when you allow too much flexibility, you lose all of your ability to infer anything. You actually have to assume a fairly restricted range of possible internal rotation profiles. And there, with that restricted range of profiles, you can do inference. But if you allow it to be like an arbitrary rotation profile, you get nothing out. I remember now. We actually did publish that with Tanner Wilson is the first author. He's a PhD student at Monash. So that was his first paper. We published it like maybe 2 years ago. It's called Constraining Rotation Profile of Red Giant Using Spot Measurements. So it's just, those details are buried in that with an unrelated title.
Thank you. I'll stop. Yeah.
Okay, good.
All right, yeah, we're at the hour. It's
Oh, okay.
noon, so I think this is a good place to wrap up. But like I said, Earl's still around, so feel free to sign up to meet with him. And yeah, thanks again.
Thank you.
Unfortunately, we'll have to leave today. Have to get my visa for the Japanese conference, but I'll see you tomorrow.
Okay, great.
Great talk.
Thank you so much.